What up, Sci Fam? It's your boy Nickel, and today we're going to look at this term, this type of force we call gravity. So we will define the term gravity. Make sure though that we start by actually putting a title on our page, title it gravity. We'll define gravity. We'll use a couple of images to kind of show how the force of gravity changes and has different properties about it. And we will also look at the force of gravity on planet Earth. Now, one thing that I wanted to add to this page that I had to add into my margins with like a little bubble here is something that we'll talk about at the very end. So just know that you might have to add something in your margins of your page as we finish off this science notebook page. So let's get started. Let's drop into it. Gravity. Let's begin by defining this term, gravity. And now that we have a little basis of physics, we can discuss gravity in terms of how it is involved as a force and what it is as a force in science. So, like I said, it is a force which causes, it's an interaction between two bodies typically. It could be more than that, but it's typically going to, when we look at it, it's easiest to look at it how gravity is going to be impacted between, or how it's going to change between two different bodies, meaning like things out in the solar system or the galaxies. So we look at these and they have to be huge, meaning that they have to be massive. So when we think about mass and weight, we can't really measure the weight of a planet or of a moon. So instead we're going to use mass, and we'll call these massive bodies because of this idea of mass. So you have to have a lot of mass in order to have a noticeable amount of gravity. So gravity is a force which causes two massive bodies to be attracted to one another. Now this is an important property of gravity, is that it's a force of attraction, meaning that the two objects are going to be attracted toward one another. Now some other forces, such as like magnetism, if you think about a magnet, it can have a force of attraction where it pulls, or two magnets get stuck together. But you could also flip the magnet, one of the magnets around, and then you have a force of repulsion, meaning that they push each other apart. Gravity is a force of attraction, meaning that the two things would be pulled together, or they would be attracted to one another based on this force of gravity. All right, so as I discussed, when we look at the mass of an object, we have to look at massive bodies. So if we go out into space, Albert Einstein called space, he liked to use this term fabric of space and time. You see, you have to think about space and time together because, for example, if we both went to the mall, we're going to the same space. But if I went there on Tuesday and you went there on Friday, we're there at a different time. So space-time is this idea of a place and a time. And Albert Einstein used this idea of a fabric to be able to kind of illustrate what it's like when we look at how massive bodies affect space. So massive bodies are going to actually warp space-time as though it was a piece of fabric. So something like the sun is going to have a large impact on the space-time. It's going to create a big well or a divot there in space-time. Whereas something like the Earth might have less of a divot or a warping of space-time. And the main reason for this is because of their mass. So something we want to add here is that if we increase mass, like if we have something like the sun, then we increase, let me respell that, we increase the force of gravity. And the opposite is true as well, that if we decrease mass, like for in this example, the Earth, then we end up decreasing the force of gravity. So yes, all of us humans have our own mass, but our mass is so small that our mass would not warp space-time. But something like the Earth, which also has a small mass compared to the sun, will decrease the force of gravity compared to the more massive sun, which has a bigger change in gravity, or it has more gravity because of its mass. All right. So let's summarize that and say that the mass of the object warps that thing that we called space-time. creating the force of gravitational attraction. You see, it's a force of attraction because if I were to place an object on the space-time continuum here, or the fabric of space-time, it would naturally want to be attracted to this object. If I were to place something like the moon out here, it also would be attracted to that object because it's on that slope. So let's take this random planet, or we'll call this maybe a sun or something. We'll call it Sun A. So let's say Sun A is here. Let's look at how this is going to warp space-time. Let's say it is very massive. So you can see it warps space-time. Now if I were to place some planetary bodies out here in the orbit around it, or maybe at different distances from the object, you can see that the actual slope here is going to change. And so since the slope changes, then the force of gravity is going to be different. If we had a ball that was just sitting on a surface like this, compared to this, compared to this one, compared to this one, we would expect that object to move at different rates. So what we find then is that as you increase the distance, meaning that you get further from our Sun A here, as you increase the distance from the object, gravity, that force of gravity, will have less force of attraction. Remember, it is a force of attraction. So we're going to continually write that in there to remind ourselves that's a force of attraction. So this object would be less attracted to planet A than this object would be, because this one here, we'll call this planet Z and planet Q. Planet Z is much further away than planet Q, so therefore planet Z has less attraction, because if we look at this dashed line here, which represents the fabric of space-time, it doesn't have as steep of a slope that would cause that attraction to be greater, whereas planet Q has a much steeper slope, which causes it to be more affected by gravity, where gravity has a bigger effect on planet Q. So the opposite is true as well, that as you get closer, or if we use the same language as above, if we decrease the distance to the object, as you get closer to the object, or as you decrease the distance to the object, then you guessed it, gravity will have more force of attraction. All right, so what we're learning here is that gravity depends on the mass of the object. Something that has more mass is going to create more gravity. It's going to have a bigger warp in space-time. And if you're next to something that is a massive object, then it's going to affect you more than if you're further away. So as you increase distance, then you decrease the force of gravity. As you decrease distance, you get closer, then you increase the force of gravity when you get around an object that warps space-time. So gravity depends on the mass of an object and the distance away from the object that you are. All right, well, if we think about Earth, Earth definitely has gravity. So on Earth, let's look at what the force of gravity is here on Earth. Now, we are very close to the Earth, obviously. So we are closer, so therefore there is the biggest force of gravity possible because we're on the surface of the Earth. The Earth is literally keeping us here. We are staying on the Earth because of the force of gravity. So on Earth, the force of gravity is equal to 9.81 meters per second squared. And it doesn't matter where you are on the planet, whether you're at sea level or you're up on a 14er or you're up on Mount Everest, which is like 29,032 feet or something like that. No matter if you get further from the planet on the mountain, it's still not far enough away for gravity to really have much of a difference. So no matter where you are on planet Earth, as a human, on the surface, the force of gravity on all objects is 9.81 meters per second squared. So that means if you dropped two objects, like let's say we drop a baseball and we drop a bowling ball, both of these objects are going to fall to the Earth at a rate of 9.81 meters per second squared. Now, what we need to add here underneath our underneath this portion here where we say on Earth, the force of gravity, we're going to say on all objects because it doesn't affect other different objects differently. Every object is affected by gravity, and all objects will accelerate towards the Earth at a rate of 9.8 meters per second squared. Or we could say that the Earth actually is moving toward the object at 9.81 meters per second squared. That's a crazy thing to think about because the Earth is actually traveling around the sun, so it's the Earth that's pushing into our feet. Craziness. All right, so what this means then, that little thing that we need to add into the margins here, even here I'm finding a tough spot to add it, but I'm going to add it right here, and I'm just going to write that all objects, whether it is a baseball or a bowling ball, or a human, or an apple, all objects are going to fall to the Earth at the same rate. That is stunning. So I'm just going to put some emphasis around this, and you should add this into the margin if you need to, but this is an important thing to remember, is that all objects fall to the Earth at the same rate. And there are some great videos out there that I'm going to be happy to show you to prove that this is a truth. All right, y'all. That is the end of our Gravity Science Notebook page. I'll catch you on the next video. Peace.